Question 25. Capacitor network is given, values are also given. So this network we can open like this. Then we can draw an equivalent circuit. So here, capacitor C4 can take here the terminal. Then afterwards, the two capacitors C2 and C3. So this is the first equivalent circuit. Now from this equivalent circuit, you can see that C2 and C3 are connected in series, each of value 200 picofarad. So C23, when you solve, you will get 100 picofarad. Now using that, we can draw the next equivalent circuit. So here again C4, capacitor C1 and capacitor C23. Now from this equivalent circuit, we can see that the capacitor C1 and C23 are parallel, and C1, 2, 3, the total value will be again 200 picofarad. Now the next step, we can have next equivalent circuit. We can have C4 and C1, 2, 3. They are connected in series. As they are connected in series, here we can calculate the total capacitance. So the series connection of 200 microfarad and 100 microfarad we can calculate, so that you will get the total capacitance of the circuit. So once you get the total capacitance of the circuit, then we can calculate the remaining factors like voltage, current, voltage, charge, etc. So the total capacitance. Now finally we know we will get a single capacitor here. That will be the effective capacitance, and the value of effective capacitance will be around 200 by 3 picofarad. And across this capacitance only, in fact, the effective capacitance only, the 300 volt power supply is connected. So we got the effective capacitance. Now in the next step, what we have here, you can calculate what is the charge in this capacitor, for which we can use the formula Q is equal to CV, and find the value of charge. When you get the value of charge, okay, using this formula, you can find the value of charge. Now this charge Q, actually you will get, okay, now just go back for this series combination. And a series combination, you know, for a series combination, charge remains constant. So whatever charge you got here, the same will be the charge across C4 and C1, 2, 3. Therefore, we can calculate here the charge Q4, you can calculate from here. Once you get the value of Q4, next you can calculate the value of V4. How to find V4? V4 is equal to V4 is equal to Q4 divided by C4. So you got two answers now. And once you got V4, okay, you will get around 200 volt here. Remaining voltage is across C123, that is 100 volt. Now again go back. We got here the voltage is 100 volt. That is the voltage across C123. Once you get the voltage across C123, you can see C1 is an individual capacitor here. So what is the value of V1? In a parallel combination, we know voltage remains same. So that will be 100 volt. So you will get a 100 volt. And once you get V1, then you can find the value of Q1. Q1 is equal to C1 into V1. Then next, again you can go back. The voltage between C2 and C3 is 100 volts. And C2 and C3, either you have to calculate once again the voltage between C2 and C3 is 100 volt and C23 value is 100 picofarad. You can calculate the charge here. And again series combination charge will be same. So using that charge value Q2 and value of C2, you can calculate the value of V2. But in this particular question, both these are equal capacitors. 100 volt is the voltage there. So we can say voltage will have equal voltage will have for both the capacitors. V2 is equal to V3 is equal to 50 volts. And using this, you can calculate Q2 is equal to Q3 is equal to C2 into V2 or C3 into V3. Q3 is both will be same. So you will get the voltage and the charge across each capacitor. Now next question 26. Parallel plate capacitor, area is given, plate separation, voltage, how much electrostatic energy is stored in the capacitor. So electrostatic energy U is equal to half CV square is equal to half into C is epsilon naught A by D into C square. So you will get the answer. Then next, obtain the energy per unit volume. Energy per unit volume is energy density. Energy per unit volume. Hence, arrive the relation between U and magnitude of electric field. You have the formula energy density small u is equal to half epsilon naught E square. Equation we have already derived. Okay, and E is equal to V by T. That also, you know, electric field is voltage divided by plate separation. Now, next question 27. 4 microfarad capacitor, take it as C1, 200 volt V1 disconnected from the supply, and another 200 microfarad capacitor uncharged. That means V2 0, C2 is equal to 2 microfarad. And how much is the loss of energy in the form of heat and electromagnetic radiation? During sharing the charge, energy will be lost in terms of in the form of heat and electromagnetic radiation. Again, loss of energy formula we know C1 C2 into C1 C2 into V1 minus V2 the whole square divided by 2 into C1 plus C2. So substituting the values, you will get the answer. Now, next, show that the force on each plate of a parallel plate capacitor has a magnitude equal to half QE. where Q is the charge on the capacitor and E is the magnitude of electric field between the plates. Explain the origin of factor half. Usually, in electric field, there is a charge, then force F is equal to QE. But here, between the plates, we are asked to prove that it is half QE. Okay. And we need to explain what is the reason we got that additional term 1/2 there. So here we have a capacitor, okay, and just assume that this capacitor plate is slightly moved away from each other. So actual plate separation is D, but an additional separation delta X, one of the plates is positive, other one is negative, they will attract each other. Applying force against that attraction, just move this plate towards this point for a distance delta X. So what we have to do, we need to do work against attraction. So that work done to separate the plate by delta X. Okay. Work done to separate the plate by delta X. We can calculate. That is delta W is equal to F delta X. Delta W is equal to F delta X. Then increase in volume of the capacitor. Increase in volume of the capacitor is equal to A is the area of the plates and delta X is the plate separation. So increase in volume is equal to A into delta X. That additional increase in volume, how much is this particular volume? That is it is plate area A into additional separation delta X. Then increase in potential energy. Increase in potential energy. Potential energy per unit volume is half epsilon naught E square in capacitor. So that is potential energy per unit volume. So increase in potential energy is equal to into volume into delta X. And what is the source of this increase in potential energy? Actually, we have done work. That work is stored as increase in potential energy. Therefore, we can write as F into delta X is equal to half epsilon naught E square A delta X. Now, delta X cancel on either side. You will get the equation for force. F is equal to epsilon naught E square A divided by 2. That's equal to, we can make small rearrangements. So you will have epsilon naught A divided by 2 into E square, we can write E into E, and one of the E's we can write as V by D. Now you will get epsilon naught A by D. Epsilon naught A by D, we know capacitance C. E, one E is remaining, then V divided by 2 is equal to, again we know CV. CV is Q, so QE by 2. Therefore, force between the plates of the capacitor is QE by 2. So that is the proof. Now we need to give an explanation why you are getting QE by 2 instead of QE. The reason, when you take a capacitor plate here, you can see electric field inside the capacitor, electric field is present, but outside the capacitor, electric field is 0, which we have already proved discussed all these factors. So when you take a particular plate, what is the average electric field acting on a single plate of the capacitor? The average electric field will be E average is equal to, the left side it is 0, right side it is E. Therefore, average will be E by 2. So, average electric field acting on each plate of the capacitor is E by 2, not E. That is the reason in the equation for force, we have, instead of QE, we have Q into E by 2. So, that way we can give the explanation for the factor half. Now, come to question 29. Question 29. Okay. The figure you can see. Two shells are there of radius R1 and R2. Then charges are there. Just we will calculate what is the potential difference there. The potential difference V is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught Q divided by R2 minus Q divided by R1. One of the charges will be induced charge. Q divided by R2 minus Q divided by R1 is equal to 1 by 4 pi epsilon naught Q into 1 by R2 minus 1 by R1. 1 by R2 minus 1 by R1. Now, we can take LCM here. Afterwards, use the formula C is equal to Q by V. After taking LCM here, this value of V you can substitute here. When you substitute, you will get this equation. Okay, equation represents the capacitance of a spherical capacitor. Now, come to question 30. The same spherical capacitor. Okay, inner radius, outer radius, all these factors are given. The space between the concentric spheres is filled with a liquid of dielectric constant K. So, K is equal to 32. Determine the capacitance of the capacitor. So, how can you calculate the capacitance of the capacitor? You have to use this formula. C is equal to 4 K into, because dielectric constant is there, K into 4 pi epsilon naught R1 R2 divided by R1 minus R2. You will get the value of capacitance. Now, part B, what is the potential of the inner sphere? The potential V is equal to Q by C will be the potential of the inner sphere. Then compare the capacitance of this capacitor with that of an isolated sphere. Explain why the latter is much smaller. If you take a sphere, capacitance of a sphere, it is much less than the capacitance of the spherical capacitance, which we discuss in question 29 and 30. So what is the reason? Here you can see the outer sphere is earthed. Outer sphere is earthed. You remember the theory of parallel plate capacitance. If when you take a single capacitor, its capacitance is very less. So we keep a parallel plate and the second plate is earthed also. So the earthed plate will reduce the potential of the first plate so that you can store more charges. The topic you have studied as the theory of parallel plate capacitor. When the second plate is earthed, you can store more charges. The situation is same here also. Instead of a simple sphere, its capacitance is very less. But you have a sphere with an outer shell, and the outer shell is earth. Once the outer shell is earth, the capacity of the sphere will increase. So this is the answer of part C. Now, next question 31. Two large conducting spheres carry charges Q1 and Q2 are brought close to each other. Is the magnitude of electrostatic force between them exactly Q1 Q2 divided by 4 pi epsilon naught r square, where r is the distance between their centers. Whether you can apply Coulomb's law or not for a large conducting spheres, that's the question. So if you have large conducting spheres, you take the spheres like this, large conducting spheres. Now separation distance r is between their centers. That is the value of r. But here what happens, when you bring both the spheres close to each other, the charges will repel each other and the charges will be aligned in this way. There will be rearrangement of charges. Afterwards, it is not the uniform distribution of charge. So what happens? The distance between the charges is no longer r now. Therefore, it is not possible to use this equation. Because when spheres are brought close to each other, the charge distribution becomes non-uniform. So we cannot take the separation distance as the distance between the centers of the sphere. Now, next, if Coulomb's law involved 1 by RQ dependence, would Gauss law be still true? No. We know we derived Gauss law using Coulomb's law. If Coulomb's law itself is different, then Gauss law is not satisfied. Then next, a small test charge is released at rest at a point in an electrostatic field configuration. Will it travel along the field line passing through that point? Okay, will it travel along the field line passing through that point? You have to understand field line. What is field line? Field line represents the force acting on a test charge by the source charge. So, force, the test charge moves because of the force from the source charge. Now you can think force means it is related to acceleration. So as it is related to acceleration, we know always an object travels in the direction of velocity. Object travels in the direction of velocity, not in the direction of acceleration. But here, field line represents the force, acceleration. Therefore, it is not necessary that it has to pass through exactly along the field line. Field line represents acceleration, but particles travels along the direction of velocity. Then next, part D. What is the work done by a field of a nucleus in complete circular orbit of an electron? What is the orbit? What if the orbit is elliptical? Anyway, it is a closed path. Closed path. Work done by a conservative force to move a particle along closed path is equal to 0. If it is circular or elliptical, whatever, always you get it 0. Part E, we know that electric field is discontinuous across the surface of a charged conductor. Is electric potential also discontinuous? No. You know that electric potential is present inside the conductor. A charged conductor, the potential inside is constant. As potential inside is constant, the potential has no discontinuity. Field has discontinuity because there is no field inside a conductor. Now, next, what meaning would you give to a capacitance of a single capacitor? If you take a single capacitor, where is the second plate? That's the question. The second plate is supposed to be at infinity. The second plate is at infinity. Now, next, is a possible reason why water has a much greater dielectric constant, because water molecule is asymmetric. That is the reason. Water molecule is asymmetric. Due to asymmetry only, it has very high dielectric constant, and you can try to remember the value of dielectric constant of water also. It is 80. Next, question 32. Data is given there. A cylindrical capacitor. The cylindrical capacitor, spherical capacitor, etc. You can just remember that solely. Okay, it is not in detail in your syllabus. So cylindrical capacitor formula you can just remember. Capacitance C is equal to 2 pi epsilon naught L divided by 2.303 log R out divided by R in. 2.303 means outer radius and inner radius. That is the formula. Okay, if you can remember just that formula, that is enough. Otherwise, no need to go into details. Now, next question 33. Question 33, voltage is given 1 kilovolt. Dielectric constant K is given 3. Dielectric strength, what is the meaning of dielectric strength? The maximum electric field that can be applied on a dielectric. If you apply more than that, then what happens? This electric field will remove the electrons from the atoms and dielectric property will be lost. So the maximum electric field that can be subjected to a dielectric, we call the name dielectric strength, that is 10 power 7. And the question says that the electric field should be 10% of dielectric. So we will give only 10% of maximum capacity. Therefore, electric field will be 10% of 10 power 7. That is 10 power 6. And the capacitance is given 50 picofarad. These are the data given there. Now, what is the minimum area? So we have to take capacitance C is equal to K epsilon naught A by D. C is equal to K epsilon naught A by D. But D is not given in the question. So D you can calculate using the formula E is equal to V by D. But when you substitute the value, you have to take 10 power 6 only for electric field, 10% of dielectric strength. From here, you find the value of D. After getting the value of D, substitute in this formula and find the value of area, required area. Then next, describe schematically the equipotential surface corresponding to a constant electric field in Z direction. A constant electric field in Z direction. So a uniform electric field we have to take, that's only. We take a uniform electric field like this, and the electric field is acting along Z direction, E, which is in Z direction. Now, a constant electric field means you will have the equipotential surfaces like this. They are equidistant. You have to take care when you draw the diagram. Okay, you have to draw better than what I have drawn here. The surfaces should be at equal distances because you have studied equipotential surface at equal distance in uniform electric field. These distances should be equal when you draw the diagram. Equal distances should be there. Now, next, a field that uniformly increases in magnitude but remains constant direction. Again, the idea is same only. So here, uniform electric field. But the strength of the electric field increases. If strength of the electric field increases, then what will happen? We have equipotential surfaces in this way. And if the electric field strength increases in the sense, we can see the surfaces are coming close to each other. Not the size of the surface, okay? The surface relative distance between them coming close to each other. So like this. When the electric field is stronger, equipotential surfaces are close to each other. And in both these cases, you can see the equipotential surfaces are in XY plane, perpendicular to Z axis. Equipotential surfaces are in XY plane. Then next, a uniform grid consists of long, equally spaced, parallel, charged wires. A uniform grid. So uniform grid we can draw like this. The positive wire and the negative wire, and the electric field is acting like this. Uniform electric field from positive to negative. Uniform electric field, and equipotential surfaces are perpendicular to electric field. Equipotential surfaces perpendicular to electric field. The surface will be like this. Again, the field is uniform, so they are at equidistant, and you can give reference with the help of axis. So like this. These are the equipotential surfaces. Now, next, come to question 35. Van de Graaff generator. Of course, Van de Graaff generator is not in your syllabus, but you can see the data given there. Spherical metal shell. Voltage is given. Then dielectric strength. Again, I repeat, the maximum electric field is given. Then what is the radius of the shell? So a direct substitution is enough. So again use the formula E is equal to V divided by D or V divided by R. From there you find the value of R. That's it. Find the value of R. Then next question 36. A small sphere of radius R1, charge Q1 is enclosed by a spherical shell of radius R2 and charge Q2. Okay. Show that if Q1 is positive, the charge will necessarily flow from the sphere to shell. This we have already proved in the theory. Okay, if a charged sphere is placed inside a charged shell, and always sphere is at a high potential, so that always charge goes from sphere to shell. Okay, the theory already we have done this proof, that is in the topics 2.16. The topic is 2.16. Already the proof we have done. Of course, it's a part of anti-graph generator which you need not study, but this proof already we have discussed. Now, question 37. So, a lot of charge is coming towards Earth. Still, we are not getting any shock, an electric shock. What is the reason? That's the question. Because we are, wherever we present, it's an equipotential surface. So whenever there is a potential difference, then only charge will flow through our body and we will get the shock. So far we are in equipotential surface. Throughout our body, the potential is same. So there is no flow of charge, there is no shock. So we are in equipotential surface. Then next, man fixes outside his house an aluminium sheet over an insulating slab. Will he get a shock? He will get the shock because lot of charge is coming towards Earth. So as this aluminum sheet is placed over a non-conducting support, the sheet will be charged and there is a possibility of getting shock. Then next, discharging current towards atmosphere. Okay, a lot of current is coming towards atmosphere. Then why then does the atmosphere not discharge itself completely? Okay, why can't it discharge completely and becomes neutral? That's the question. Okay, in other words, what keeps the atmosphere charged? So the atmosphere remains charged because of the continuous flow of charge from, specifically from sun. So solar flares and a lot of charge is emitting from the sun. So continuously the charge is coming towards Earth and getting neutralized also. So there is an equilibrium between these two. The charge coming towards the Earth and the charge gets neutralized. Because of that equilibrium, the atmosphere remains charged always. And part D. Okay, what are the forms of energy into which electrical energy of atmosphere is dissipated during lightning? Okay, during lightning you have heat energy, sound energy, and light energy. Heat, light, and sound are produced due to the electric discharge during lightning. Okay, thank you.